Welcome to this presentation. My name is Mark Scythian. The date today is November 17, 2025. So in this presentation, we are going to solve for the DC voltage, current, and watts power across nodes A, B here in the circuit. So notice that we have a series circuit coupled with a parallel R3 junction for which the circuit terminates into its function and then flows back to ground. So the first step is we have to combine the two parallel resistances at R3 and the 100 ohm load using the inverse sum rule for combining parallel resistors. So we get a combined parallel resistance of 90.91 ohms. So that will behave as if it is a series resistance. So when we calculate the total resistance on series, we just add the resistances up together. And it should be noted that DC electricity flows from positive to negative or positive to ground. And also, current will remain constant on series pathways. We will only incur voltage drops on series. So all we need to do is add up the three resistances, including the combined resistances, to calculate a total resistance of 2090.91 ohms. Next, we can access Ohm's law, which states that Ohm's law for DC electrical circuit states that voltage E is equal to current I measured in amps times resistance R measured in ohms. But we need to know the current that discharges out of the positive terminal. So we can simply divide both sides of that equation to solve for current. So current is equal to voltage divided into resistance when working with DC circuits. So we can improve on this and rename I as I sub T. The total current is equal to E sub T, total voltage, divided into R sub T, the total resistance. So we know the total voltage is 24 volts. We divide this value into the total resistance. And we calculate a current discharging from the positive terminal of the battery of 0.0115 amps and remaining constant across the series pathway, including the combined resistance of 90.91 ohms. So we have total voltage, 24 volts, total resistance, 90.91, and a total current for the circuit of 0.0115 or 11.5 milliamps. So now we can use Ohm's law once again to calculate the voltage drops at resistors 1 and 2. So we can just simply multiply the constant current times each resistor's value across R1 and R2. So we get a voltage drop of 11.5 volts at R1 and R2. And then we can also multiply the constant current from discharging from the positive terminal times the combined resistance. So the third voltage drop and the combined resistance at R3 junction with our 100 ohm load is 1.05 volts. So series circuits maintain constant current with voltage drop. So with series circuits, the current is constant and the voltage is the variable, and just the opposite with parallel circuits. So when finding voltage drops in series, we can use E is equal to IR, and then current drops on parallel, I is equal to E over R. Because parallel circuits maintain constant voltage, the voltage drop at the R3 combined resistance will also project across to the voltage across the 100 ohm load. So there's only 3 voltage drops, but there is a constant projected voltage to the 100 ohm load equal to also 1.05 volts. So we'll write that in for the voltage across nodes A, B. So to prove that this calculation is correct, we have to obey Kirchhoff's rules for circuit equilibrium, which states that all the voltage drops in series when added together will equal the total voltage. So indeed, we have 24 volts as the sum of the series voltage drops. So that's been validated as correct. So we do the same thing across the parallel pathways, but note that the current will not remain constant across the parallel pathways. The current will actually split. Only the voltage remains constant. So we can use the Ohm's law equation for solving for current and rename it as the current at R3, IR3, is equal to the voltage 1.05 volts divided into the 1000 ohm resistor value at R3 with respect to a parallel junction. So we calculate this current value for R3 and then 1.05 volts over 100 ohms. So this subsequent current value for 100 ohm load. So if we add these two together, they should equal the total current obeying Kirchhoff's rules for circuit equilibrium with respect to current. And indeed, the calculation was made correctly. So now we can just convert the current across AB from whole amps into milliamps by multiplying it times 1000. So we get 10.5 milliamps across nodes AB. And then lastly, we can calculate the DC electrical power in wattage, which is equal to the I current times the E voltage. So that's just simply the whole amps across AB, which is 0.0105 amps or 10.5 milliamps times 1.05 volts. So we get this very tiny wattage value across AB, for which we convert to milliwatts by multiplying it times 1000, and that would be 11 milliwatts. So we'll just finalize the answers. So calculating the electrical circuit data mathematically supersedes instrumentation. Thank you for watching this presentation and have a great day.